Okay, welcome to this new course on fundamentals of transport processes 2. This is a follow on course to the earlier course on fundamentals of transport processes 1. So, that course should be considered as a prerequisite for this course. So, those of you who have not gone through that course, there are certain things there that we will be using in this course. Okay, so, I would urge all of you after this lecture to go and look back at what all we did in that course to bring yourself up to date with all the material that was done. So, in this lecture I will just try to reiterate some of the important concepts that we developed in the first course on fundamentals of transport processes 1. Okay, so, okay, so that is the name of our present course. In the first part, we looked at the transport mostly of mass and energy in chemical systems. The motivation for that was that whenever we talk about some process which converts some raw materials into some useful finished products, we require raw materials to be converted into products. So, if we have some raw material A which is going to some product B, we can do the experiment in a test tube of course and convert A to B. This might require some additional heat energy to be put in order to facilitate the process, some heat energy to be taken out if it is an exothermic reaction. However, when we run this, when we try to produce this on the large scale in economically feasible ways, in order to produce large amounts of chemicals, we run into the difficulty that you need to make sure that the reactants get to the place where they have to be converted, the products leave, and the amount of energy that is required is supplied at that particular location. And all of this requires that in addition we also need to provide some way of mixing the products and the reactants. Okay. So, we took in the first in the fundamentals of transport processes 1 3 prototypical cases in which we discussed each of these processes. One was a stirred tank reactor with some fluid in it, in which the product came in, I am sorry, the reactant came in, the product left, okay. And this stirring was necessary in order to mix the entire system. Now, this was an inhomogeneous reaction. So, you had some catalyst particles there which were catalyzing the reaction. Okay. Now, for the reaction to take place, the reaction actually takes place on the catalyst surface. Okay. For this reaction to take place, it is necessary to ensure that at the location where the reaction is taking place, the reactants come in, the products leave, and there is also sufficient supply of heat energy in case it is an endothermic reaction or sufficient removal of heat energy in case it is an exothermic reaction. Okay. So, the transfer of mass of the reactants to the surface at the location locally where the reaction is taking place, the transfer of products out from the surface, the transfer of energy in or out of the surface, these are essential for making sure that the reaction takes place as designed. Okay. Similarly, in this case you also have some kind of a stirring taking place, there is some kind of a circulation of fluid, and that circulation of fluid takes place because of this impeller. At the impeller surface itself, it is necessary to make sure that there is sufficient momentum transferred to the fluid, so that the fluid is stirred. And that is a process of momentum transfer. the shear stress that is exerted by the impeller on the fluid causes the fluid to rotate, and this transfer of momentum ensures that sufficient mixing takes place that these reactions can be carried out. Okay. In a similar manner, we took the example of a heat exchanger, okay, a shell and tube heat exchanger. Okay. In this case, you have a shell side and a tube side, okay, and let us say hot fluid comes in, okay, at the tube side, and cold fluid goes out, okay, and cold fluid comes in and hot fluid goes out. Okay. In this case, the heat is coming in with the fluid that is coming in, which is at a higher temperature. Okay, the fluid that is coming in is at a higher temperature. The fluid that is going out is colder. The heat is coming in with the fluid. Okay, that heat is transferred across the surface of the heat exchanger to the outer shell side fluid. Okay, and this heat is carried out by the shell side fluid. Okay. So, heat is coming in on one side, heat is going out on the other side, okay. And however, this heat has to be transferred across the surface. And if we look at the surface itself, okay, we find that there is one fluid that is passing through over here, there is another fluid on the other side, and this heat has to be transferred from this fluid to this one. Okay. And that transfer has to take place perpendicular to the direction in which flow is taking place. Okay. So, this is a problem of heat transfer. Okay. And of course, we also considered the case of a spray dryer. Okay. If you go back and recall in that previous lecture, we had a spray dryer, okay, which was spraying little droplets of some, okay, food product, okay, and these droplets were cooling and drying as they came down. Okay. If you recall, this example was done for the particular case of a spray dryer where you have some food products which are sensitive. So, the difference in temperature between the hot air that is coming in and the droplets cannot be more than a certain amount, and for this reason this dryer has to be very large. The droplet has to travel a long distance before it dries. And if you look locally at the surface of a droplet itself, okay, at the surface of a droplet itself, the heat energy has to first go in, and it has to evaporate the water within this droplet, and once it evaporates this water has to now come out of the droplet. And this is a combined process of heat transfer of heat in, the latent heat required for evaporation of the water in the spray dryer, and mass transfer out, okay, the mass that comes out because the water has evaporated, in order to give you a dry powder, okay, after the spray drying is over. Okay. So, these were prototypical examples that we took. Okay. Each of these cases there is a flux of either heat or mass going in or going out of some surface. Okay. There is also transport, okay, due to the fluid that is coming in itself. Okay. So, for example, in the previous reactor example, there is transfer along with the fluid of the reactants in at this point. There is transfer of reactants in along with the fluid. There is transfer of products out along with the fluid. However, if you look at the catalyst surface itself, there is transport that is happening perpendicular to the surface. Because the surface is impenetrable, the fluid itself cannot travel perpendicular to the surface. However, there is a transfer of mass and heat perpendicular to the surface. So, that motivated us to distinguish between two dominant mechanisms by which transport takes place. One is convection, and the other is diffusion. Convection is the process by which transfer takes place because of flow of the fluid that is carrying either the mass or the heat. Okay. in these examples that we took, okay, the convection is the heat that is coming in with the heat exchanger at the inlet over here. Okay. The heat that is coming with the heat exchanger. Okay. Heat that is leaving the heat exchanger with the fluid. Okay. These are both convective transport processes. Okay. In this case, in the spray dryer case, for example, heat is coming in with the gas that is coming in to dry the droplets, and water is of course going out because it gets collected by the gas. Okay. The water vapor gets entrained by the gas and it leaves along with the gas. So, that is transport along with the fluid itself, that is convection. Similarly, here flow in of reactants at the inlet is convection, products out is convection. Okay. And similarly, if you have some heating or cooling that is taking place of the entire reactor itself, okay, that is getting carried, okay, along with the fluid either at the inlet or the outlet, that is convection. The transport that takes place perpendicular to the surface, not due to the mean fluid flow, is diffusion. Okay, so, convection is due to mean flow of fluid carrying mass or energy. Okay. Diffusion is not due to mean flow, okay. It is due to molecular motion. Okay. So, it is a molecular process. In a fluid, you have molecules which are in rapid fluctuating motion. The average energy of the molecules is of course given by the equipartition of energy. Okay. So, we know very well that for the molecular velocities, the equipartition rule holds for the translational velocity is half m v square is equal to 3 by 2 k T. Okay. And we had calculated some of the gas velocities in the previous course. The velocity of the gas molecules is comparable to the velocity of the speed of sound in that particular medium. So, in air, for example, sound travels at around 300 meters per second. Similarly, the molecules of the gas themselves have fluctuating velocities of the order of 300 meters per second. In hydrogen, it is a little larger because the mass of hydrogen is much smaller, it is about 2000 meters a second. In denser gases, it will be less, okay, but that is roughly the magnitude of the fluctuating velocities of the molecules. So, these molecules are all in fluctuating motion. Now, if the concentration of some reactant product were uniformly spread throughout, the molecules of that would also be in fluctuating motion, and on average molecules has equal probability of moving upwards or downwards, and therefore, on average you will have no net motion of molecules. Okay. However, if there is a gradient in the concentration, we took the specific example in the last class of the transport between two bulbs. Okay. You have a carrier gas, okay. The molecules are in fluctuating motion, and you have a trace constituent, okay, which has a higher concentration on one side than on the other side. We assume that the concentration of this trace molecule is sufficiently small that the motion of these molecules do not shift the center of mass. Okay. So, in that case, what is going to happen if you look at some particular region here, okay, I have a surface here, okay, and I have molecules that are in fluctuating motion. And if I have a concentration gradient of this trace solute, okay, if there is a variation in concentration of this trace solute, okay, I can plot the concentration as a function of this distance from the surface. I can plot the concentration as a function of distance from the surface. Okay, so, let us just take this off. Okay, so, I have the surface here. and if I plot concentration as a function of distance from the surface, okay, I will have some variation in concentration across the surface. Okay, there will be some variation of concentration. So, the concentration on top here is higher than the concentration below. Okay. Now, the molecules themselves are in fluctuating motion. Okay, they travel with equal velocities both upwards and downwards. Okay, so, there is no preference for traveling in any particular direction. However, the concentration of molecules is higher on the upper side. So, on average you will have motion of molecules from the upper to the lower side. Okay, so, this is my distance y. Okay, so, this and this is the concentration C. You will have on average the motion of molecules from the upper to the lower side. Okay. It will go from region of higher concentration to a region of lower concentration. Okay. And this process is called molecular diffusion. Okay. And this is responsible for the transport of both mass, momentum and energy, okay, in these fluid systems. Now, we had estimated what is the flux of molecules due to this diffusion process. Okay. The flux was defined as J, okay, is equal to mass transported across the surface, mass transported across the surface per unit area per unit time. Okay, that is the amount of mass transported across the surface per unit area per unit time. Okay. So, that is related to the way in which the concentration varies across the surface. Okay. The relationship between these two is what is called Fick's law of diffusion. Okay. So, in the simplest form, the way that it is written is that the flux J in the x direction is equal to minus d delta C by delta x. Okay. So, let us look at this in a little more detail. Okay. Let us say that I have some particular element of fluid here, okay. Okay, a slab of fluid, okay, in which I have different concentrations on the two sides of the slab. Okay. I have a difference in concentration delta C across the slab. Okay. The distance across which there is this difference is delta x, okay, and this cross sectional area of the slab is A. Okay. Now, obviously, the amount of mass that is being transported is going to be proportional to the area itself. If I have more area, I will have more mass transported. So, it makes sense to define the mass transported per unit area per unit time as the flux. Okay. So, that is why I defined the flux as the mass transported per unit area per unit time. Now, the mass transported per unit area per unit time has to decrease as the distance between the two ends becomes bigger. Okay. So, it has to be inversely proportional to the distance delta x. Okay. So, this is the equation for the Fick's law for diffusion. Okay. And all flux, so this basically says that relates the mass transported per unit area into time is equal to a diffusion coefficient. Okay. Diffusion coefficient times change in mass density. Concentration is a change in mass density. Okay. Density divided by the distance across which that change takes place. Okay. Divided by the distance across which that change takes place. Okay. Mass density has dimensions of mass per unit volume. Okay. Mass density has dimensions of mass per unit volume. So, on the left hand side I have mass per unit area per unit time, right hand side mass per unit volume divided by distance. Okay. That means that the diffusion coefficient has dimensions of length square T inverse. Okay. This is true for all diffusion coefficients. Okay. In the case of heat transfer, instead of mass, okay, instead of mass I substitute heat. Okay. So, my equation for the thermal diffusion becomes heat transferred per unit area into time is equal to the thermal diffusion coefficient alpha times change in energy, change in energy density divided by distance. That is, energy density is the energy per unit volume, the thermal energy per unit volume in that fluid divided by distance. Okay. And once again, the thermal diffusivity has to have dimensions of length square per unit time. And if you recall, we had made obtained a relation between the thermal diffusivity and the heat conductivity as alpha is equal to k by rho Cp. Okay. Similar is the case with momentum diffusion. Okay. Momentum diffusion will be the focus of this second part, where we will deal with the transport of momentum, the equations for the transport of momentum in fluids. Okay. So, I will come back to that a little later. Okay. Now, this diffusion coefficient, it has dimensions of length square per unit time. Okay. From microscopic arguments, we had derived the values of this diffusion coefficient in gases. Okay. If you recall, we had seen that the diffusion coefficient is proportional to the root mean square of the gas molecular velocities times the mean free path, which is the distance between molecules in a between collisions in a gas. Okay. And physically, that comes about because if I have a diffusion process and if there is a concentration gradient, of some trace molecule, okay. The molecules that cross this surface come on average a distance of mean free path from above the surface. Okay. They come on average a distance 1 mean free path above the surface. Okay. They come downwards. Okay. And because they come downwards from a distance of the order of mean free path, the concentration, the number of molecules coming downwards is proportional to the concentration at this particular position. The molecules going upwards come from a distance of the order of the mean free path below the surface. So, they come from a distance, a significant location distance below this surface. The concentrations at these two regions, these two places are different, and they differ by a value that is proportional to the gradient. Okay, let me see. Not delta c by delta x, okay, where delta x is this distance, okay, times lambda. Okay. So, this distance is of the order of lambda, this is of the order of lambda. The difference in concentration goes as lambda times delta c by delta x. The net exchange is proportional to the number density times the concentration itself times the fluctuating velocity. Okay. Therefore, you find that the diffusion coefficient is given by Vrms times the mean free path. Okay. This is true for gas molecules. In gas molecules, energy transfer also takes place due to the motion of the gas molecules themselves. And so, the thermal diffusivity and the mass diffusivity are roughly of the same magnitude. The other thing to note is that in both of these cases, mass transport takes place down a temperature gradient. Okay. So, if the concentration on one side is higher than on the other side, there will be transfer taking place from the higher concentration to the lower concentration. And for that reason, we have this negative sign here in all of these equations, okay, for both heat and mass transfer. Okay. So, there are two mechanisms that we had studied, convection and diffusion. And the next step is to actually use these two mechanisms in order to find out what is the transport rate, okay, of mass, momentum and energy. Okay. Now, that was done by a process that was called shell balances. Okay. Basically, you write down a balance equation, because mass has to be conserved, energy has to be conserved, momentum has to be conserved. Okay. So, therefore, the conservation equation was of the form change in mass, momentum, energy in time delta t, okay, is equal to in minus what leaves. Okay. Okay, plus any accumulation that may be there. Okay. Within this differential volume. Okay. So, this was the basic principle, okay, the conservation of mass momentum energy. Okay. And this was done by using what was called shell balances. Okay. So, the simplest case, okay, let us say that you had a flat plate, okay, with some concentration, and it was transporting mass momentum energy into an infinite fluid. Okay. So, for example, initially the temperature everywhere T is equal to T infinity, and at time T is equal to 0, T is equal to T naught at the surface. So, you instantaneously heat the surface at time T is equal to 0. Okay. So, at some later time energy gets conducted into the medium, and then you get some particular energy profile as you go further into the fluid. Okay. How do you find out what this is? Okay. So, the way to do that is to construct a small, okay, first you use a coordinate system, okay, z perpendicular to the surface, and you look at a thin slab of material, okay, delta z, okay, it is called a shell, okay, and you write down equations for the energy coming into this shell, energy going out of this shell, okay, the accumulation, in this case there is none because energy is only coming in and going out. Okay. Change in energy in a time delta t is equal to the energy in minus energy out. Okay. And by doing that calculation you end up with the diffusion equation for the temperature field. Okay. So, over an instant of time delta t for this shell of thickness delta z, you find that the change delta t by delta t, okay, over this time interval delta t is equal to minus the thermal flux, okay, the variation of the thermal flux over this time, delta j the energy flux. Okay. So, we will just call it as the heat flux. Okay. Where Qz is the energy traveling in the z direction, okay, because only the energy traveling in the z direction, okay, at the lower surface increases the energy of this volume, that traveling in the z direction at the upper surface decreases the energy of the volume, and for that reason you find this negative sign. Okay. So, this is the simplest case. Okay. You do a shell balance and you get this equation for a shell of thickness delta z, the change in energy over a time delta t. Okay. And then what you do is you take the limit as delta t goes to 0 and delta z goes to 0 to get what is called a partial differential equation. Partial t by partial t is equal to minus partial q z by partial z. The next step is to express the flux in terms of the temperature itself, and that is done by the relation between the flux and the variation in temperature with respect to the z direction. Okay. So, for example, the flux is written as, if you recall, it is minus alpha times delta t by delta z, okay, the flux at any given location for a distance delta z with a variation delta t in temperature across that distance. Take the limit as delta t and delta z goes to 0, this just becomes equal to minus alpha times partial t by partial z. Okay. So, this is the Fourier's law of heat conduction, the equivalent of the Fick's law of diffusion that we had just discussed. Okay. So, with this expression for the flux, you can put that into the equation and you get the thermal unsteady diffusion equation, okay, that is partial t by partial t is equal to alpha times d square t by dz square. Okay. So, that is a thermal unsteady diffusion equation in one dimension. Okay. Similar for the concentration field. Okay. Partial C by partial T is equal to d partial square C by partial Z square. Okay. Just to refresh your memories, these symbols here, okay, these partials, they represent what are called partial derivatives. Okay. We will come back to that in this course, but I just wanted to point it out at this stage just to get things clear at the beginning. Okay. This temperature field, concentration field, they depend upon two independent variables, both z coordinate as well as time in this particular case. And because of this, when you take derivatives, one has to be clear about which coordinate is being varied and which coordinate is being kept a constant. Okay. So, when I say a partial derivative, partial t by partial t, okay, is equal to, okay, t at z t plus delta t minus t at z t divided by delta t in the limit as delta t goes to 0. Okay. An important point to be kept in mind. When I say partial t with respect to time, I sit at one particular location in space and measure the difference in temperature between two instants of time separated by an interval delta t. Difference divided by delta t is the partial derivative. Okay. Similarly, if I wanted to take a partial derivative with respect to z, this will be limit as delta z goes to 0, t of z plus delta z minus t, so let me comma t minus t of z t divided by delta z. So, I am fixed at one particular instant in time. I take two locations about this point z separated by a distance delta z, find the difference in temperature between those 2 points and then divide by the interval. Okay. So, that is what is meant by partial derivatives. Okay. So, in this particular case, this one dimensional diffusion case, we got a diffusion equation of this kind. Okay. You can extend it to other situations. For example, we saw that if you were to do the same in cylindrical coordinates, okay, so for example, the flow through the transport into a pipe, for example. Okay. So, if you wanted to look at heat transfer across the surface of the pipe, it makes sense to take a coordinate system in which the surface of the pipe is a surface of constant coordinate. Okay. In the previous case, okay, we were looking at a flat plate, and therefore, the plate, the surface of the plate itself was a surface of constant coordinate. Therefore, we used a coordinate system in which the distance from the plate was the coordinate. In this case, it is preferable to use a coordinate system in which the surface of the pipe itself is a surface of constant coordinate. Okay. And the coordinate system that is useful for this is what is called the cylindrical coordinate system. Okay. In this, there are three coordinates. One is along the axis. Okay. This can be called either the x or the z coordinate. I will refer to this as the x coordinate. Okay. And then there are two other coordinates. Okay. One is the distance from the axis. Okay. So, the distance from the axis to any location on the within the pipe is called the radial coordinate, and the angle made by this distance vector, okay, with respect to some arbitrary axis, is what is called the theta coordinate or the meridional coordinate. Okay. That is, you can take any particular plane as a reference plane. The angle made by the distance vector from that plane is called the theta coordinate. Okay. In this particular case, if the configuration is axisymmetric, that is, there is no variation as you go around at a fixed radius. Okay. If you go around at a fixed radius, there is no variation in temperature. The equation for the temperature field, the conservation equation, temperature or concentration field, becomes partial T by partial T is equal to d into 1 by r d by dr of r partial T by partial r. So, this derivative that we had is different from the derivative that we had previously, okay, because in the previous case we just had second derivative of T with respect to z square. Okay. Similarly, the concentration field, I am sorry, I should put alpha for the temperature field. And for concentration is D into and these additional terms come about because of the dependence of surface area on the distance from the axis. Okay. So, as I go outward from the axis, as r keeps increasing, right, the surface area of the differential volume also increases. Okay. So, if I have a shell at this distance, the cylindrical surface area of this shell is proportional to the radius itself. The cylindrical surface area is equal to 2 pi r. That surface area keeps increasing as you go further outward from the axis. As r increases, the surface area increases. So, even though the flux may be a constant, the amount of mass transported increases as the surface area increases, and for that reason you have to have additional terms here. It is not just a simple second derivative in the cylindrical coordinate system. We will see this again when we look at vectors and tensors. We will see how to derive this in terms of the variations of unit vectors with respect to distance when we do momentum transport. Okay. Similarly, in spherical coordinate system, okay, so for example, if I were trying to calculate the diffusion from a spherical particle, okay, it is more convenient to use a coordinate system in which the surface of the particle is a surface of constant coordinate. In this case, I should take one of the coordinates as the distance from the center of the particle itself r. Okay, I should take one of the coordinates as the distance from the center of particle. Therefore, I will be carrying out my shell balances for spherical shells. Okay. Once again, for spherical shells, the area increases as the radius increases. Here it increases as r square, because the area of a spherical shell is 4 pi r square. For that reason, I get once again a different form of the equation. Okay, in this case, I will get partial T by partial T is equal to alpha into 1 by r square d by dr of r square partial T by partial r. Okay, so, this was for a spherical shell. Okay. One thing to frame these equations. Okay, so, this basically gives me a partial differential equation for the variation of temperature or concentration, both in time as well as with respect to distance. So, that is one part of it. Second part of it is to solve these equations. Okay. And in the previous course, Fundamentals of Transport Processes 1, we had seen various ways in which these equations can be solved. Okay. Just to summarize, okay, one was what is called similarity solutions. This was particularly appropriate for the first problem that we solved, and that was the transport from a flat surface into an infinite fluid. Okay. So, T was equal to T infinity, okay, far away, okay, and we used this as the z coordinate, and at time t is equal to 0, the temperature of the surface itself was increased to T is equal to T naught. Okay. And because of that, if you plot the temperature profile, at the surface the temperature is T naught, but at the instant at which the temperature was increased to T naught, that increase in energy has not been conducted into the fluid yet. So, the temperature of the fluid was still equal to T infinity, which is smaller than T naught. Okay. So, you had a temperature profile that looks something like this. And as time progresses, conduction takes place. This temperature is still equal to T naught, far away it is still equal to T infinity. So, you have a series of curves that looks like this. Okay, as time progresses. Okay, so, this is increasing time. Okay. And in order to obtain an analytical solution for this, we used the fact that in this particular problem, okay, I can define a scale temperature and if you recall, we have to solve the heat conduction problem. Partial T by partial T is equal to alpha times. Okay. But since this conduction takes place into an infinite medium, there is nothing that we can scale the z coordinate by. Okay. There is nothing that we can scale time by, because there is no time scale in the problem. At time t is equal to 0, you increase the temperature and just leave it. There is no final time. The temperature at the surface is T naught, the temperature far away is T infinity, but there is no length scale in between. There is no fixed distance at which we have set the temperature equal to some fixed value. Just from dimensional analysis, there is only one dimensionless group that we can get in this case, okay, just from dimensional analysis, and that is eta is equal to z by root alpha t. Okay. Originally, the equation was in terms of two independent variables, time and z. Just from dimensional analysis, we reduced it to just one independent variable, and therefore, the equation now becomes an ordinary differential equation in this variable eta, okay. And on that basis we were able to solve it. Okay. So, just to reiterate, all of the equations that we get in this case, they are all partial differential equations, and there is no general way of solving partial differential equations. The only way to obtain solutions is to somehow convert these into ordinary differential equations and then solve them. And similarity solutions procedure offers one way of doing that: convert this partial differential equation into an ordinary differential equation just based upon dimensional analysis, and then get the solution for the temperature. Okay. If you recall, we had got the solution for the temperature field as T minus T naught by T naught minus T infinity is equal to 1 minus 1 over root pi integral 0 to z by root alpha t d psi e power minus psi square by 4. Okay. So, that was one way, reduce it from 2 to 1 variable using the fact just dimensional analysis and the fact that there is no other time scale in this problem. Okay. The second was what was called separation of variables. Okay. If I have a channel with one particular two boundary conditions, T is equal to T naught, T is equal to T 1 at one particular distance, okay, let us say L. Okay. In this case, there is a length scale in the problem. So, my z coordinate can be scaled by the distance L. So, I can define T star is equal to T minus T infinity by T naught minus T infinity. Okay. Z star is equal to Z by L. So, in this case, we cannot use the similarity solutions. What we do is to use a separation of variables procedure. This T star is a function of z as well as time, okay, where the scale time comes out of the diffusion equation itself. Okay, this scale time becomes T times alpha by L square. Okay. So, this is a function of two variables. We write it as some function z of z star times some function of T star. Okay. The original equation that I had was of the form dt by dt is equal to partial square t by partial z star square. Okay. And this is in scaled coordinates. So, I have already incorporated the thermal diffusion coefficient into this term here. Okay. And if you now write down, substitute this, I can reduce it to an equation in which I have 1 over f df by dt is equal to 1 over z d square z by dz square. Okay. Now, the left hand side depends only upon time, right hand side depends only upon distance, and because of that these two have to be constants, because if I keep z a constant and change time, the left hand side will change and the right hand side will not, unless both of these individually are constants. Okay. and these constants now have to satisfy the boundary conditions on the two surfaces. Okay. And we saw how to satisfy the boundary conditions. In case you are not familiar with that, kindly go and revise it once again. Okay. There are the idea basically is that we write down this T star as a sum of a set of eigenfunctions, okay, Cn sin n pi z star e power minus n square pi square t star, okay, where these functions are basically solutions which satisfy the boundary conditions only for integer values of n. Okay, these functions satisfy the boundary conditions only for integer values of n. Okay. And so, these integer values come out of the solution of the equation. They are called the eigenfunctions, and I am sorry, they are called the eigenvalues, and these functions themselves are called the eigenfunctions. These functions satisfy what are called orthogonality relations, okay. And these orthogonality relations enable us to determine what these constants are. Okay. In this particular case, the solution turns out to be T star is equal to 1 minus z star, the homogeneous part. Okay. I should change the definition here, because I have two different temperatures. Okay. So, the definition here is actually T minus T naught by T 1 minus T naught, okay. And this T star becomes 1 minus z star minus summation over n of 2 by n pi sin n pi z star e power minus n square pi square t star. Okay. So, that was the second solution procedure. In case you are not familiar with this, as I said, we will be using this in the course once again. So, kindly go back and familiarize yourself with this procedure. Basically, once I have done this transformation, okay, I get a differential equation for each of these, and each of these has to be a constant. Okay. So, each of these has to be a constant. The constant has to be negative, because I require that f has to decay to 0. Okay. If f is just the transient part, this has to decay to 0 as time goes to infinity. Okay. And also it has to satisfy the boundary conditions on these two surfaces. On the basis of that, I get this as minus n pi the whole square. Okay. Yeah. And also we looked at oscillatory flows, okay, oscillatory systems where you have an oscillatory variation, a time periodic variation. Okay. Okay, that was done for the particular case of a pipe flow. In that particular case, you can, since the equations are linear and since the forcing is oscillatory, the response also has to be oscillatory. Okay. So, you can assume an oscillatory function for the time dependence. Since you already have the oscillatory function for the time dependence, you get an ordinary differential equation for the spatial dependence, and that was also something we did in the last class, in the last course. Okay. That is not something we will be using in the present course, so I will not talk too much about that. Okay. After that, we went and we determined equations which are general, okay, which hold for any particular differential volume. Okay. So, the first was for the Cartesian coordinate system. Okay. In this particular case, you have planes as surfaces of constant coordinate. We took a small differential volume in here, okay, of width delta y, delta x, delta z, okay, calculated what was coming in and what was going out, okay, both due to convection, due to fluid motion, as well as due to diffusion, the diffusion fluxes. Okay. And we obtained balance equations in all three coordinates simultaneously. Okay. These equations were of the form partial c by partial t plus the derivative of the velocity in the x direction times concentration, okay, the derivative in the x direction, plus d by dy of UIC. Okay. This was equal to the gradients of the fluxes minus partial Jx minus partial j z partial z. Okay. We had started defining vectors in that previous course. Okay. We had defined the vector flux j is equal to j x E x plus j y E y plus j z E z. Okay. Velocity vector okay. We had also defined a gradient vector okay. E x times d by dx plus E y okay. Here I will use E x, E y and E z instead of I, j and k to represent unit vectors. Okay. So, E x is a unit vector in the x direction, E x, E y is in the y direction and E z is a unit vector in the z direction. This is just more convenient notation for us for this course. So, we will be using this. Okay. With these definitions, you can write this equation as partial c by partial t plus del dot, the dot product of this operator and this vector u times c. C is a concentration, is a scalar, u is a vector velocity. You multiply u and c, you get a vector. Take the dot product of this divergence with this one. Okay. So, that is basically the other term on the left hand side, d by dx of u x c plus d by dy of u y c plus d by dz of u z c. Okay. The right hand side I have minus dot product of this once again this gradient operator with the flux vector j. Okay. The dot product of the gradient operator with the flux vector j. Dot product of gradient operator we will see is what is called the divergence. Okay. Now, the flux itself can be expressed as the gradient of the concentration field. Okay. I can write the flux itself vector as minus d times the gradient of the concentration field, okay, because this is equal to minus d times E x dc by dx plus E y dc by dy plus E z dc by dz. Okay. And this on the right hand side I just substitute minus d times gradient of c and I get d del square c. Okay. So, this was the general equation in a Cartesian coordinate system. Okay. This was the equation in a Cartesian coordinate system for a cubic differential volume. This form of the equation is far more general. Okay. This form of the equation is far more general. It holds for any coordinate system. Okay. It holds for any coordinate system. Only thing is that these operators, the divergence operator, this del square operator called the Laplacian, they are different in different coordinate systems. Okay. So, that is the only difference. Okay. We had also explicitly derived constitutive equations in both cylindrical and spherical coordinate systems. Okay. Just to refresh your memory, in the cylindrical coordinate system there is an axis and the distance from this axis is what is called the radius. Okay, so, if I have some point here, the height above the xy plane is the z coordinate, the distance from the axis is what is called r, and the distance, the angle that r makes with any particular axis is called theta. Okay. And in this case you have to take a cylindrical shell, okay, a cylindrical shell that has surfaces of constant coordinate. Okay. Okay, so, it will have 6 surfaces just like the cubical differential volume, it will have 6 surfaces, 2 of which are perpendicular to the r coordinate, that is the one on this side and the one on the other side, the inner one, 2 of which are perpendicular to the theta coordinate, that is on the right and the left, and the 2 of which are perpendicular to the z coordinate, top and bottom. Write the differential equation, write the conservation condition, change in mass in the differential volume is equal to mass in minus mass out, and you get a differential equation for the cylindrical coordinate system. Okay. And that has the form partial c by partial t plus del dot u c is equal to d del square c. Okay. Where in this case del dot is equal to 1 by r d by dr of r r, take this out, urc plus 1 by r partial by partial theta. Okay. So, this is the definition. Okay. And the del square operator was 1 by r d by dr of r. Okay, let's write. Okay. We had derived these expressions explicitly from shell balances in part 1. Okay. Similarly, we had also done it for a spherical coordinate system. In this particular case, there are 3 coordinates. One is the distance from the origin. This is called r. The second is the azimuthal angle, the angle made by the radius vector with any particular axis. It is generally chosen as the z axis, that is theta. The third is the meridional angle, and that is the distance made by the projection, okay, of this radius vector onto the xy plane with any axis traditionally chosen as the x axis, and that is phi. Okay. And in this case, once again these operators are redefined. Okay. So, del dot u c is equal to 1 by r square d by dr of r square u r c plus 1 by r sin theta partial square c by partial phi square. Okay. And finally, we have the del square operator in this coordinate system as del square c is equal to okay. Okay. So, those are the Laplacian and the divergence operators in the different coordinate systems. Okay. So, that is where we were, and the next lecture I will take some time to motivate what we are going to do in this course in the context of what I have just discussed for the previous course. This is the background, kindly go through it again in case you are not familiar with it. Okay. It is important that those who are for understanding the next part of the lecture, that you are familiar with all of this. Okay. And I will motivate in the next lecture what we are going to do next. Okay. So, we will see you there.